Quartz cannot make 90-degree angles. There to there. All diamonds exhibit a sort of corner that looks like a box, like the corner of a box. And that's what you see. You see a line here. But these two are the X and the Y axis. Okay? A three-dimensional thing. And the way that these form is with all the little carbon atoms all line up together on these two axes. And where they cross right here in the middle is the Z-axis. And when you look down there, it splits the view into four different things. And that's because of the crystal structure of a diamond. And it looks cubic, sort of, but hexagonal here, sort of, but not really. It's not a perfectly even hexagon, but it's even closer to a perfect hexagon than quartz crystals usually are. But none of them, no quartz crystal can have a 90-degree angle. They can't have it. It's not like it's sometimes one way and sometimes another. It's the way atoms fit together. It's these are all the same size atoms, and so they fit together in rows and columns. They're all the same size. They line up together, and just like little soldiers, man. They're all the same. Quartz is made from silicon dioxide. It's actually a silicon atom surrounded by 4 oxygens. And it creates a four faces and 4 sides that are triangles that fit together. And that tetrahedron, 4-sided figure, is what makes all quartz crystals look the way they do. And they don't look like this. They can't make tapers. They can't make right angles. They do not have planes of cleavage. And that's what you see in there. That's what you see. Those are planes of cleavage. And they're thin. They're absolutely microscopically thin, because it's the arrangement of carbon atoms inside a carbon molecule. This is a single molecule of carbon. And the easiest test in the world is with a ruby. And probably I don't have one handy. Oh well, hang on. And here we go. We got the ruby. Look at that ruby, huh? That's a pigeon blood ruby from Myanmar. This is harder than this. This is a diamond, because only diamonds scratch, rubies, or sapphires. All of these were sold as quartz. Nobody checks. Because you see something like this, and then you think about that little thing on people's fingers. The one that cost $10,000 or whatever. And then you look at this, and then you think about that, and it ain't fucking funny, man. People get hosed when they buy diamonds. For sure, man. Except me, I'm, because I actually know what I'm buying. I do actually test things, usually. And I've been laughing for years at people saying, "Yeah, there's magic in those quartz crystals." I thought, no, man. I know what quartz crystals are. They don't do nothing, man. I thought they were crazy. Now they think I'm crazy because I'm telling them it's not quartz, it's a diamond. That's why it does all those cool things. That's why they light up when you hold them. That's why they're light kind of feeling. Like when you measure the difference between this and this is about twice as heavy per cubic centimeter as this is, because this is just carbon. It's just carbon. It's all carbon atoms. And carbon is lighter than aluminum and stronger than steel times a bazillion. I can use this as a hammer. Bam, 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 bam. And the diamond tip just stays there because of that double covalent bond. Carbon atoms and silicon atoms are the only ones that can do that. Carbon is on one end of a solid solution series. Silicon dioxide is on the other. Silicon carbide is in the middle. And that's the stuff. And this is even actually brighter and sparklier than diamonds. But it doesn't cut up nearly so pretty. Not really something you want to hang around your neck. But it's cool to look at. It's also 10 on the Mohs scale of hardness. And I know that because once I switch hands, I can test this. Go like this. And I know what this is then, because it's a 10 on the Mohs scale of hardness. This came out of China. It's one of the really cool things I've been buying from China. And I love this stuff, man. This is, I mean, it's like one of those things you look at it and go, wow, how wonderful life is when you have stuff like this, man. It's not worth $1 bazillion. It crumbles, crumbles into little pieces. But it's really, really pretty. This is strong, strong, strong. Doesn't break. Doesn't wear out because of that double covalent bond. We make tools with these that don't wear out. We can make bearings and bushings that don't wear out. You don't have to build machines that break. That's a real waste of energy and time and resources. Resources that don't belong to us. They belong to our children. Diamonds can be used for bushings, bearings, building machines, structural use. I have big pieces that we can cut into structural things, and it's a strong as steel, okay? Mining steel, taking it out of the ground. You take iron, and then they smelt it, and they use coal. And it pollutes at every step of the way, from getting it out of the ground and transportation, and then smelting it, and the coal industry to support that. These things we can pick up and slice them with diamond wires in micro-thin chips, or in structural sized panels. And it's already there. You don't have to do anything to it except cut it to the right size. And they're not little. They're like the size of buses and stuff. Big. And it's carbon. I know it is. I know it is because the last few times I went out to this mine, I went and checked. I started carrying one of these little guys, and I use it. And when I can't scratch it easily, I don't know if you watched me there, but that was just barely touching it. But my diamond scratches that ruby every time. It'll scratch anything except another diamond. Here it just skates. Just skates. And it's a unique feel. I know it's like an ice skater. That's what it reminds me of. And so when I go out there, I do these tests And the result is that this stuff here forms with this stuff here. This is carbon, this is silicon carbide. And I have a piece with diamond, silicon carbide, and a layer of opal, all on the same stone. I don't know where that one is. I've been real sick. We will find it, no doubt. See that with the different viewpoints? That's because of all those rows and columns inside the structure of the stone. And when we cut them, we try to cut them with the angle of those things going like this, and you can see it right there. Boom, boom. And it catches the light. That it catches the light, and you can see also there's a tesseract in the middle. It's a hexagonal tesseract. That's magic indeed, because that is a mathematical space inside that crystal caused from the reflections inside the stone. Isn't that cool? And people thought they were quartz, and I thought they were nuts. But they're not quartz. They're diamonds. And they're not rare. They're very common. They are ubiquitous. They can help us save the earth. It's not what they can do in a rich man's finger. It's what they can do for us with the industry and science from resources that do not require tremendous amounts of pollution to produce. We're going to change the world.